Good evening. Let's wait for a couple of more minutes and let others join. Then we'll start. Okay, I think we can start now. So, good evening, everyone. My name is Umair Hussain, and I'm a PhD scholar from the Department of Mechanical Engineering, IIT Madras, under the PMRF scheme. And I welcome you all again to the doubt session of the Basics of Finite Element Analysis Part 2 course, and which is a continuation to the Basics of Finite Element Analysis Part 1 course. So in the previous course, let me remind you that we studied the basic aspects of the finite element analysis, and further we studied how to solve 1D problems using finite element analysis, and understood the basic structure of the procedure that we undergo in the FEM process in the FEM solution. So this course is a continuation to that course. So we in the first week we studied the basic the we revised the concepts of the previous course, and then in next week we started with the error approximation. So we studied the causes of various error, and based on that we classified them, and then we studied the methods to evaluate those errors. Uh, uh, so, can anyone just remind me what sources of error we studied last time? So that was week two.
We studied L2 error and H1 error.
Yeah, but I am asking the sources of error. That's a way to compute them, right?
Yeah, there are many sources of error which we studied in the last lecture that depend upon the approximation function which we consider. maybe it with
Right.
linear or quadratic, or also it is due to material property the error can arise. This is what I recall from the last lecture.
Okay, good. Very good. Yeah, so what Mr. Salman told, that's right. And apart from that, we studied geometric approximation error also. And other type of error was computational error. So the error, the inaccuracy that comes while we compute certain arithmetic operations. So that can be a manual computation or even computer-based computation. So yeah, these were the sources of error that we studied last week. So now this week we started with another main topic of this course, that is the numerical integration techniques. So in FEM, FEM is a numerical technique, right? So we studied there are various steps. First of all, there's discretization. Then we find the formulate the weak form. We assign the approximation functions, and then we solve the weighted residual statement to get the equations, and then further solve those equations to get the solution vectors. So we remember that the weighted residual statement that we have is a weak statement. So there's an integral term involved there. So basically, we need to solve certain integrations there. So manually calculating those integrations again and again is a tedious task. So, firstly, this is the main reason. This is one of the reason, and then secondly, the large scale FEM simulations that we do practically, those are not done manually, not by hand. We use computer programs to do them. So. Computer programs in computer programs, it's not very trivial to solve the integrations analytically. So we incorporate certain numerical integration techniques to get those integral values. So suppose we have some random function with suppose this function shown here in black line. This one exact solution shown here. I hope my screen is visible, right? So suppose we have some random function which we need to integrate between the limits x say to xp. So the we in the starting of this course we learned about this approach, that one thing we can do is we can estimate this function by various type of simple functions, like we can map this as a linear curve. So we take 2 points, one sorry take 2 points, one at the beginning here and another point at the end, and we just map that as a linear function. So integral is basically the area under this curve. So how can we find the integral between this straight line here? It is basically the area of this trapezoid, right? This trapezoid. Uh, Likewise, we can replace this linear curve with a quadratic curve or a cubic curve, and that would increase the number of points here. So if we have a quadratic curve, we have 3 points, two at the ends and one this one here. And further, if we want to increase the point, we can do that. So, if it's a linear approximation, I told you that the integral is basically the area of this trapezoid, which is shown here. So, this type of approximation, we know that this is called trapezoidal rule. And if we increase the number of point to 3, then this is the way that we get the area under that curve. So, this is known as the Simpson's rule. So basically, for to get the integral values for these, we need two things. Firstly, we need the value of the function at each point, and then we need to know the step size, the interval length when we're calculating the integral. So this integral we can arrange in form of the function value at each point at each point multiplied by some random number known as weight, which we call quadrature weight here. So that's a generalized rule here. We can approximate an integral numerically by evaluating the value of that function at various points, multiplying by some weights. So that's a generalization of different types of rule that we use to numerically integrate. So these points here are known as quadrature points, and Fi is the value of the quadrature point, and Wi is the weight of for each point. So, for trapezoidal rule, we use just 2 points, and the weights are are h by 2. H is the interval length. For Simpson's rule, we have 3 points, and the weight for each first point is h by 6, then second is 2h by 3, and third point is again h by 6. So likewise, if we have more number of points, there is some specific rule for that point, for that many number of points. So in FEM we use two special type of quadrature methods, numerical integration methods. First is Gauss-Legendre quadrature rule, and the second is the Newton-Cotes quadrature method. Of these two, this one is more famous. So I think I have never seen. Maybe there might be some solver that use Newton Cotes, but most of the solvers that are built in FEM, they use Gauss-Legendre rule. Okay, so I hope it's clear till here. These are the basic integration schemes that we numerical integration schemes that we studied so far in this week. Okay, the next thing that we studied is the natural coordinate system, natural or normal coordinate system. So, so in FEM, we discretize the the domain into different elements. So each element has different coordinate values, nodal coordinate values. So it is rather convenient to so if we solve the integration over each element separate in that original coordinate system, the values of coordinate will change again and again, and so it would be different every time we calculate this integration. So what we do is we transform this coordinate system into what is known as the natural coordinate system. So which is defined for 1D, it is defined minus 1 to 1. For 2D, they can be different ways. If it's a quadrilateral elements, the element, then it's a quadrilateral like this. So it's 0 here, then it's minus 1, 1, 1, minus 1, 1, minus 1, minus 1. So for 2D coordinates, something like that. And for triangular elements, I think mostly we use this type of triangle. This is the isopyramidal triangle. So yeah, for 2D, there are different ways we can do it. But for 1D, we have the simple 1D element in natural coordinate system like this. So we transform the our given element into this natural coordinate system. So every time our integral would look same, except for the Jacobian, and it will be different every time. So in order to transform our coordinate system from x here to zeta here, we need some mapping function. Mapping function is basically relates x and zeta. So if it's a simple 1D system, then it's a linear transformation function. We can assume any linear function a plus b zeta. So if we know for when here it's xa in this system becomes minus 1 here, and what is xb here becomes plus 1 here. So you can substitute the value in this function for wherever xa is x equals to xa, zeta equals to minus 1, and x equals to xb, zeta equals to plus 1. So we can get the values of a and b. We can for and this gives us the mapping function for linear 1D element. Okay, so I hope it's clear till here. Then we studied the Lagrangian interpolation function and natural coordinate system. So we in the previous part of this course we studied some approximation function or interpolation function, uh, but they were in the original coordinate system. Something I think it was something like p1 equals to 1 minus h by 2 to h by 2. I think it's one way or the other. Either this is phi1 or this is phi2. So similarly, we can also define these interpolation functions for the natural coordinate system. So in in the lecture we studied we generalized this the the interpolation function formula for n number of nodes. So using this formula, we can get the interpolation function for as many number of nodes as we want. So yeah, so that's a fast and easy way to get interpolation function for any type of linear 1D element. This is for 1D element, not linear, a 1D element. You can have as many number of points as you want. Okay, so there's one aspect that we studied in this week's course, that is the approximation of geometry. So in FEM, we are quite familiar that we approximate the solution. So we can approximate solution as something, right? So in 2D and 3D domain, so sorry, not in 2D, 3D, but in all the dimensions, we also approximate the geometry. Since we are transforming our given domain into its natural coordinates, the natural coordinate system, we do the same there. So excuse me. Yeah. So this is known as the approximation of geometry. So one important aspect that we studied is that these interpolation functions here. So they are known as interpolation or approximation function in general. But for in case of geometric approximation, these functions are especially called shape functions because they influence the shape of the elements. So These two functions may not be same always. But in general, in FEM, we most of the time we use the same functions. Okay, so yeah, we are back again to our main problem. That is, we need to find the integral, right? From this, we need to calculate this integral xa to xb. So how we proceed is that we first we transform the our coordinate system to the natural coordinate system, and then we use the mapping function and replace the our original coordinate variable to the transformed coordinate variable. And yeah, we change the integral. We if we are doing it with respect to dx, then we change it to the variable of the natural coordinate system d zeta. So this replacement is done by introducing a term known as Jacobian. So if we know the transformation function, the mapping function, then we can get the Jacobian. So our problem gets transformed to this. So one more thing we studied, I'll just quickly remember that revise that the number of points required in approximating the solution and the number of points required in approximating the geometry may not always be the same. Though we in practical most of the time, I think we keep them same. So if both are same, that's known as isoparametric formulation. I think it's a common term. And if our number of points for approximating geometry is less than the one number of points for approximating solution, then that's known as subparametric formulation. That is quite popularly known as used in Euler-Bernoulli beam problem. And then the other way where m is greater than n, that is known as superparametric formulation, which it is not very generally used. So again, yeah, we are back to Gauss quadrature method that we studied earlier. There are the two methods commonly used in FEM to numerically integrate. One is the most popular one among them is the Gauss Legendre quadrature formula. So one thing, so the important features about this rule is that the quadrature points are not essentially same as nodes, so they are different. If we'll see in case of the trapezoidal and the Simpson's rule we studied initially, we took the end node points as our quadrature points. We calculated the function value at those points. But we'll see that that's not the case in the Gauss quadrature formula. And another thing is that the points may not be equally spaced. That we'll see. So just like any generalized quadrature rule that we generalize a formula for that initially. Yeah, this one right here. So we generalize the general formula. So we use the same formula for calculating the integral using Gauss quadrature. But that rule has its own set of points and weight function. So we can just calculate the integral using one point. So that would be 0. By the way, one thing important is that the Gauss quadrature formula is used between the integral limit of -1 to 1. This is must. Let's add it here. So the quadrature points and these weights are actually derived in such a way to solve between this integral limit only. That's why we transform the coordinate system into a natural coordinate system. So we have for different number of points, we have different the different point values and different weight function weights. So a choice of these points actually there's a relation derived for it. We didn't study the derivation actually, but we'll just quickly know what it is. So so the choice of R basically depends on the degree of polynomial if it's a polynomial function. If it's not polynomial, I don't think we can get an exact solution for that. Maybe the error would reduce as we yeah, the error would reduce if we increase the number of points, but it will tend to zero. But I don't think we can get exact solution for all the functions. So for polynomial, the choice of R is given by these formula here. Okay. So I think that is all we studied in this week's course. So if there's any doubt, then we can discuss it now. Otherwise, we'll move on to the problem session. Okay. Yeah. If there's no doubt, then I think we can move forward. Okay. So yeah. So as we do it, as we proceed with the session every time, we first discuss the content of the course, and then we solve some problem based on that week's content. That would help you to understand the assignments. Okay, so we start with the first problem. So numerically calculate the integral 0 to pi sine x dx using the trapezoidal and Simpson's rules. Evaluate the error for each case. Okay, so we have a simple integral given here. So we have to numerically calculate the this its value using trapezoidal rule and Simpson's rule, and also evaluate the error for each case. So first we'll start by calculating the integral analytically. So that's pretty easy. If I'll be happy if I get support from the audience for this. So cos x is sin x minus cos x, right? Okay. So cos x pi minus cos x 0. Cos pi is actually minus 1, isn't it? And cos 0 is 1. So we get 2. Okay, I think that's correct. Please correct me if I'm wrong. So we use get I using trapezoidal first. So trapezoidal basically linearly approximate the solution, right? So we need formula is actually h by 2 f at 0 f at pi. So the interval length is pi minus 0 pi by 2. So sine at 0 is 0, right? And sine at pi is also 0. So we get 0. So yeah, you see there's a pretty huge error here. We use the trapezoidal rule for sinusoidal function. We know the reason, right? We'll plot the sine curve between 0 to pi here. Function value is 0 everywhere. If we connect these 2 points using a straight line, we will get 0 area under the curve. So that's why we get 0 using trapezoidal rule. Next we can use the Simpson's rule. Simpson's rule formula was, can someone tell me the formula? H by 6 sine. So we have 3 points, right? We'll distribute into equal 3 points. Sine 0 plus 4 times sine pi by 2 plus sine pi. Okay. So again h is pi by 6. Sine 0 is again 0. Sine pi by 2 is 1 and again 0. So we get 2 pi by 3. Just to check how close it is, let me use my calculator. That gives us 2.094. So yeah, that is pretty close, right? So in this case, error is 0.044 compared to the error in trapezoidal rule minus 2. It's pretty huge. Okay, so I hope this was clear. Then we can move on to the next problem. Okay, so you need to find the linear mapping function for mapping the domain 2, 6 to the natural coordinate system. So we have our domain here. We have an element here, which is x equals to 2. Here it x equals 6. So we need to transform it to the natural coordinate system. So what are the values at two coordinates of the natural coordinate system? Can someone tell me? So what would be the value at these two nodes here? This and this and this. Sorry. Okay, since I'm not getting any response. So zeta is -1 here and +1 here. Fine. So we need to find this transformation function. So you need to find linear mapping, right? So we assume a linear function between x and zeta. So we know at x equals to 2, zeta equals to -1. So we substitute this into the equation above. 2 equals to a plus a minus b, right? And at x equals to 6, zeta equals to 1. We write 6 equals to a plus b. We add up the two equations, we get 8 equals to 2a. This means a is 4. So substitute the value of a here. Get 6 minus 4 equals b. This means b equals 2. So our mapping function become x equals 4 plus 2 zeta. Okay, fine. Okay, if it's fine, then we can move forward. So now again we have a domain. So now this domain is varying from 6 to 2. It's kind of a reverse of the previous one. I need to transform this to a natural coordinate system. Right? So again we use the same assumption of linear mapping function. So this time at x equals 6, we have zeta equals -1. So this gives us 6 equals a minus b at x equals to zeta equals 1. So we have 2 equals a plus b. We add up, we get 2a. Means a equals 8, sorry 4. Again substitute value of a here, it b equals 2 minus 4, a equals to -2, right? So our mapping functions become 4 minus 2 zeta. Okay, so there's an observation that we can see in these two solutions. Can someone highlight this? Uh, what can we observe from these two problems? You can unmute yourself and answer. Can someone tell me what I just changed in the second problem, and what can be observed from the solution? Okay. Is there anyone who want to guess? Wants to try? Okay, I think I'll tell. So what happened was that in first problem we took the domain 2 to 6, and then we in the next problem we reverse it to 6 to 2. So you'll see there's slight difference in the mapping function. So here mapping function is x equals to 4 plus 2 zeta. Here it becomes 4 minus 2 zeta. So if we take the Jacobian for this case, what would be dx by d zeta, right? We'll get 2. But for this case, Jacobian is minus 2. So we get a minus sign here. And we know a property of integration that if we have some integral from a to b of some function of x dx, this is equals to minus of, if we reverse the integral limits b to a. So this minus sign, if we reversing the domain and mapping it to the same natural coordinate system, this minus sign would reflect in from the Jacobian. So here it was plus 2, now we're getting a minus 2. So that's how this thing is this minus sign is incorporated while we are reversing the integral limits in an integration. So I think it's a pretty cool concept. If there's any doubt, you can ask me now. Okay, if there are no doubts, I think we can move forward. Okay, we need to find the Lagrangian approximation function for 5 nodal element. So the formula for Lagrangian approximation function was quite straightforward. So I told that we studied that we can it's easy to find shape function for as many number of nodes as we want. So we can try that. We'll not calculate all, but we'll try to calculate all some of the shape function for a 5 noded element. So I can recall the formula was beta minus beta 1. So yeah, then beta minus beta 2, beta minus beta I minus 1, zeta minus zeta I plus 1 till the end point tan divided by zeta I minus zeta 1, zeta I minus zeta 2. The same here. Just replace zeta by zeta I. So for 5 noded element, how do we what would be the coordinates of each of the 5 nodes? Can someone answer this? So we have 2 nodes here in the middle. So what would be the coordinates of each node? Zeta 1, zeta 2, 3, zeta 4, zeta 5. Okay, anyone? Okay, so since it's the natural coordinate system varies from -1 to +1, so we have, and between we have 0, here we have -12, here we have +12. So we can try writing shape function for I equals to 1. Skip the first term, start with zeta minus zeta 2, zeta minus zeta 3, zeta minus zeta 4, zeta minus zeta 5, zeta 1 minus zeta 2, zeta 1 minus zeta 3, minus 4, minus 5, minus 1 plus half is minus half. Then we have -1 minus 0 is again -1, -1 minus half is -3/2, -1 minus 1 is -2. Zeta, zeta minus 1, zeta square minus 1 by 4 upon, we get 4 minus sign becomes plus, okay, 2 to cancel, we get 2 by 3, 2 by 3. So that is the shape function for first node of this element. So likewise, we can try and find the approximation function for other nodes also. Tedious task. We'll try for one more. I think. Take up 2. So it's minus zeta plus 1 coming from zeta minus 4 is half. Zeta minus half. Okay, zeta minus 1. Zeta 2 is minus half. Minus half minus, minus half plus 1 is half. Then we have minus half minus 0 is again minus half. Minus half minus half is minus 1. Minus half minus 1 is minus 3 by 2. So there's no space here. So we get 8 by 3, sorry, minus 8 by 3. Okay, we can get 8 by 3, 1 minus zeta square, zeta, zeta minus half. Okay, so this is the shape function for second node. So likewise, it's pretty trivial. We can go ahead and find the shape function for other nodes also. So if this is the simple formula-based problem, there shouldn't be any doubt here. If yes, please let me know. Okay, if there's no doubt, we can move forward to the next problem. So we need to find the mapping function using the shape function for linear 1D element problem and 2. So problem 2 was we had the element x equals to 2 to 6, and we need to map it to the natural coordinate system. So x equals to 2 here, x equals 6 here. You need to map it to beta equals to -1 to beta equals to +1. So we need to use shape functions to find this mapping. So can someone tell me the relation for the approaching the geometry using shape functions? Okay, so since we know the solution approximation is using I equals 1, 2, right? So likewise, geometric approximation done using this relation. So we have, since we want a simple linear 1D approximation mapping, so we use only, for linear element, we have only two nodes. So we can write this as psi1 x1, psi2 x2. So what are the shape functions for 1D element, 1D uh, element in natural coordinate system? So what is the general formula? It's zeta minus zeta 2 on zeta 1 minus zeta 2. So zeta 2 is plus 1, so we have zeta minus 1 upon zeta 1 minus zeta 2 is minus 1 minus 1 minus 2. So psi 1 is half of 1 minus zeta. Then psi 2 is zeta minus zeta 1 on zeta 2 minus zeta 1. Get zeta minus minus 1, that is zeta plus 1, and zeta 2 is 1 and zeta 1 is minus 1. So 1 minus 1 is 2, half of 1 plus zeta. So these are the shape functions we have. So we can simply substitute the values here to get our mapping function. So x is 1 minus zeta by 2 times x1. x1 is 2 plus psi 2 is 1 plus zeta by 2. So x2 is 6. So we get x equals to 1 minus zeta plus 3 plus 3 zeta. We get x equals 4 plus 2 zeta. So I think that we got that. So yeah, this is the mapping function here, 4 plus 2 zeta, and we'll check what we got there. Problem 2, right? So right, yeah, 4 plus 2 zeta. So we can see that these are the two ways in which we can get the mapping function. So through both of them, we get the same answer. And we need to find the Jacobian. We did that right before also. So Jacobian is dx by d zeta is 2. So we can also check this method on the third problem. So there we changed our uh, domain from, we'll do it here. That there we change our domain from x equals to 6 to x equals to. We'll apply this here. So we have 1 minus zeta by 2 times. Now x1 is 6. Yes. 1 plus zeta by 2 times. Now x2 is 2. So x equals to 3 minus 3 zeta plus 1 plus 2. We get x equals to 4 minus 2 zeta. Right? 4 minus 2 zeta. That's the same thing we got here. And we reverse it on. Again, the Jacobian we did calculate it would be dx by dt zeta equals to minus 3. So we can verify the claim that we made earlier there again with this in this problem using a different solution method. So I hope this was clear. If there's any doubt, you can ask. So if there are no doubts, we can move forward. So the next problem is we have to integrate the function 4x cubed minus 3 between the limits minus 1 to 1 using Gauss quadrature rule. So before using Gauss quadrature formula, we need to determine how many number of points that we would be using. That is the value of r. So does anyone remember the formula for r? Sorry, can someone tell the formula for r? Okay, so I think we have r equals to p plus 1 by 2. That is if p plus 1 is even, right? So p plus 1 is a hair even. So this is our p. So 3 plus 1 by 2, we get 4 by 2 is 2. So we need two Gauss points to evaluate this integral accurately. So for r equals to 2, what are the Gauss points? So yes, I think minus, plus minus root 3 by 2, something like that. Just check. Yeah, plus minus 0.5773. And weight function was 1 and 1, right? Yeah, 1 for both. So the integral minus 1 to 1 for x cube minus 3 dx can be roughly approximated as, so let's say this is fx. The value of f at minus 0.5773 times 1 plus value of f at plus 0.5773 times 1. So this is equal to, let's solve it here. So this is 4 into minus 0.5773 cube minus 3 plus 4 into 0.53 cube minus 3. So I'll just use my calculator for this. So we have 4 times minus 0.5773 whole cube minus 3 plus 4 times 0.5773 cube minus 3. That gives us minus 6. Okay, these two terms would cancel out, right? Just check if I made any mistake. We can do one more thing. We can just evaluate this integral manually. Minus 1 to the power 4 is 1, and minus 3 into minus 5. Okay, so we have minus 2, minus 4 is minus 6. Nice. So we got exact solution here. We can try with the r equal to 1. So we'll see if we get any error with lesser value of r. So for r equals to 1, we have just 1 point, that is 0. And we have one weight, that is 2. I hope that's right. Yeah, 0 and 2. So our integral becomes the value of this function at 0 times 2. We have 2 times, so function is 4 times 0 cube minus 3, which again gives us minus 6. Nice. So seems this function is pretty trivial, and we get an exact solution here at an even lesser value of r. So I think the solution is already converged for r equals to 1, and even if we try it for more value of r, 3 4 points, then we'll get the same answer, minus 6. So we're already getting an exact solution here. Okay, I hope it's clear how to use Gauss quadrature method to solve this integral. You can ask if there is any doubt. Okay, so if there's no doubt, we can move forward. Okay, so we have a function, and we need to calculate the integral between the limits minus 1 to 1 using Gauss quadrature rule. Again, now the highest degree of polynomial is 5. So R is given by, we have 5 plus 1, 6. So we need 3 points. So for R equals to 3, what are the Gauss quadrature points? 0, 0.774. Just use 0.774. Plus minus 0.774. Then we have weights 0.888555. So Eagle is given as function value at 0 times 0.888 plus function value at minus 0.774 times 0.555 plus function value at plus 0.774 times 0.555. So function value 0. The value of function at 0 is just 5. 888 times, we'll take this common. So function at minus 0.774 is 5 minus 6 times 774 square plus 5. Then we have the value of function at plus 0.774. So we have 774 to the power 5. Then we have minus 6 times 0.77 square. Again we have 5. So I think here we have minus some number to the power 5, and here we have plus some number to the power 5. They will give us same value with different sign. So these would cancel out. It's pretty straightforward. Then we have 5 times 0.888 is 4.44. Then we have minus 6 times some number square. This would give us positive value. This would also give us value. This would give us minus 12 times 0.774 whole square. Then 5 plus 5 is 10. So minus 12 times 0.774 square plus 10 is 2.811. So we get 6.000105. Okay, so this is the value of integral using 3 Gauss points. I'll just verify this using my calculator, the actual value of the integral. to the power 5 minus 6 times x square plus 5 to minus 1 to plus 1. Yeah, so exact value is actually 6. So we get pretty close value using Gauss quadrature. I think we could have got exact, but we did some approximation in the decimal places of the weights of the these Gauss points. So that's why we got some little error, but it's quite very less. So we can check this one again with just one Gauss point. So if we try it with r equals to 1, our integral is 2 times value of f at 0. So value of f at 0 is 5. We get 2 into 5. It's 10. So this value is pretty off. Quite far from the actual value. It's the error of minus 4. 4 actually. So we can check with r equals to 2 also. It's possible. I equals minus 0.5773. And weights are 1, right? Yeah. So minus 0.5773 to the power 5 minus 6. 0.5773 to the power 2 plus 5, and again we have 0.5773 to the power 5 minus 6 into 0.5773 square plus 5. So these two terms would cancel out, and then we have minus 12 times 0.5773 square plus 10. So what do we get? Again we get very close value. 0.00696. Some more different places. So yeah, with r equals to 2, again we get pretty close value, but with r equals 3 it's very much closer. Again, if you calculate using r equals to 4, it would be uh, the result would have been converged. So I hope it is clear till here. If there's any doubt, you can ask now. Otherwise, we'll move forward. Okay, so if there are no doubts, we can move forward. So now we have some different function. So now we don't have a polynomial. So there is no point in calculating R. We don't know P. So we have an integral here is minus 1 to 1 e to the power x square dx. And I think it's not very easy to calculate this integral analytically. So again, we'll start with r equals to 1. We have x equals to 0 and weight equals to 2. So our integral becomes 2 times value of e at 0. So the value function at 0. So this becomes e to the power 0. This is 2e. Right. Check what 2e gives us. It's around 5.436. Now we change our value of r to 2. We have x equals to plus minus 0.5773, right? Yeah, 5773, and our weights are 1 for each. So our integral becomes 1 into e to the power minus 0.5773 square plus 1 into the power plus 0.5773 square. So again, square makes the negative number also positive. So we left with 2 times e to the power 0.5773 square. So let's see what are we getting here. 2 into e to the power 0.5773 square. Oh, good. 2.791. I hope I did it correct. I'll just check. To the power minus square plus e to the power 0.5773 square. Yep, that's right. E to the power minus 0.5773 square plus e to the power plus 0.5773 square. Okay, yeah, that's the answer. So we get pretty much great difference if we increase the value from r equals to 1 to 2. This here and this here. Next we'll try with r equals 3. Our weights become 0 plus minus 0.774. And weights are 0.88 and 55, right? Weights are 0.888 and 0.555. So our integral becomes e to the power 0 plus 0.555 times, just take them common, e to the power minus 0.774 square plus e to the power plus 0.774 square. Again, they both becomes equal. So we have 0.888. I'm sorry, I did something wrong here. It's not 2 e to the power 0 becomes 1, right? Yeah, yeah. So I expect you guys to correct me if I make any mistake. So this case as 2. So with 1 point we get the value 2, and with 2 point we get 2.791. Okay, again we have 0.88 times 1 plus 0.555 times 2 times e to the power 0.774 square. I'll use my calculator for this. Plus 0.555 into 2 into e to the power 0.774 whole square. 0.888.555 times 2 times e to the power 0.774 square. Okay, this time we get 2.908. So yeah, again the value change for I equals 3. So just to check the which of these values is closest, so I'll just use my calculator to get the integral for this, the actual value of the integral. E to the power x square integrated from -1 to 1. Okay, so the analytical value is 2.9253. So you see that as we started with integral, the value of integral from with 2 by using r equals to 1, then it approached closer to the solution, the actual solution, as we increase the value of r to 2, it's 2.791, and then again if we increase the value of r equals 3, we get even more closer, 2.9087. So we can see that as we increase the number of quadrature points, we get even more accurate result. So I hope this was clear. If there are any doubts, you can ask now. Okay, so if there are no doubts, we can move to the next question. Okay, so I remember this question was given in the assignment, and I checked the solution for the assignment. There was no explanation given for this problem, right? So I thought it would be a good idea to discuss this in the session today. So if there's anyone who would like to give its answer before, if anyone has solved this problem before, you're welcome to answer it before I solve it. Otherwise, I'll move on to the solution. So no one solved it. Okay, so we're giving a triangular element here, and we're giving the equation of the lines of the triangle, and we need to find the interpolation function of this triangle. So I think in the class in the lecture so far we have not looked up much into the 2D problems. But this is a 2D problem, but however the concepts are all the same that we discussed in the class so far. So we need to find the shape function at node 1, right? The interpolation function psi 1. So what is one? What are the properties of the interpolation function? Can someone tell me? Anyone? So one of the property of interpolation function I'll write here is psi I xi xj is equals to delta ij, right? So which means if it is 1 if I equals j and 0 at if I is not equal to j, which means that psi 1 is always going to give a value 1 uh, at node 1, but on node 2 and 3 it is going to give a value of 0, right? So it's if we're talking about linear functions only, so it would be it would linearly, you can imagine it as a plane having a value of 1 and linearly going to 0 at 2 and 3 nodes. So if I try to give you a 3D idea, consider this triangle to be out of plane. So at this is node 1, this is 2, this is 3. Suppose value is 1. So we have, I draw bigger, it's not clear. So we have this triangle here. Consider it to be a 3D triangle out of the plane of this screen. Node 1, node 2, and node 3. So here the value of psi 1 is 1. It would gradually go down to 0 here and gradually go down to 0 here. So a, consider a plane triangle here, and you can imagine a plane which is giving a value 1 at node 1, and it is merging to the plane of the triangle at the line 2 3. So that's how it will give the value 0 at 2 and 3. So this essentially means that the function the shape function psi 1 is going to give value 0 at the line 2 3, and we know that the what else is 0 at line 2 3. We look at this function eta minus root 3 times 1 minus zeta equals 0, right? This is the equation of line. So you can see that this function is it will essentially give us a value 0 if we substitute any value from the line 2 and 3. So this means that psi 1 can be equal to some constant times, sorry, psi 1 is equal to some constant time eta minus root 3 1 minus eta, right? So in order to find the value of this constant, we just need to substitute the value of any node. So we know that at node 1, value of zeta is actually minus 1, value of eta is 0, and value of psi 1 is 1. So we can substitute these values in the equation above. So 1 equals to alpha times eta is 0 minus root 3 times 1 minus minus 1 is 2. So we get 1 equals to minus alpha 2 root 3. So alpha equals to minus 1 by 2 root 3. Right? So I'll write it. So psi 1 equals to minus 1 by 2 root 3 times eta minus root 3 1 minus eta. So this becomes one minus zeta by 2 minus eta by 2 root 3. Right? So this would be the shape function at node 1. I hope this is right. Minus plus. Okay. Yeah, I think it's right. So similar in the similar way, we can find the shape function at node 2. I mean the interpolation function. So again, the interpolation function should be such that it should give a value 1 and should be 0 on the line 1 3. So on the line 1 3 we have the equation as eta minus root 3 1 plus eta. Right? Eta minus root 3 1 plus eta equals 0. So shape function node 2 can be written as some constant times eta minus root 3 1 plus eta. So again at node 2 we have zeta equals to 1 and eta equals to 0. And psi 2 equals 1. We have 1 equals to beta times minus root 3 1 plus 1 is 2 minus 2 root 3. Beta becomes minus 1 upon 2 root 3. Okay, right. So again psi 2 becomes minus 1 by 2 root 3 times eta minus root 3 1 plus eta. So we can further simplify it as one minus zeta by 2. It's not 1 minus zeta, it's 1 plus zeta by minus zeta upon 2 root 3. Right? Different from the previous one. Right. Okay, so can we do the same thing to find shape function at node 3, right? So again, at node 3, the equation of the line 1, 2 uh, would give the value 0 at 1, 2 line. So what is the equation of line 1, 2? Can someone answer this? What is the equation of line 1, 2? It's not given in the question. Anyone? So it's eta equals 0. So we have the origin here, right, at this point. So this line 1, 2 is eta equals 0. Again, we can write shape function for node 3 as some constant gamma times eta. So at node 3, we have theta equals node 3, theta equals to 0 actually, eta is root 3. 0 eta equals root 3 and psi 3 is 1. So 1 equals gamma times root 3. Gamma equals 1 by root 3. Hence, psi 3 is eta by root 3. Right? So hence we got the three shape functions or interpolation function for the this triangular element using the equation of lines. So this was a pretty interesting problem in the assignment for week 3. Uh, I hope you would have been able to do it correctly. If there would have been any doubt, then I hope it's clear now. If there are further doubts, you are welcome to ask. So I think we are almost out of time now. Uh, so we'll stop at this problem for now. And if there's any question, I'll wait for some time. You can unmute yourself and ask. And since we have some new candidate here, uh, I would like to uh, uh, listen to your introduction and your motivation to join this course. If you'd like to tell. Okay, so if there are no doubts, then we can finish the session. And so, okay, so thank you so much for joining this session for the course of Basic Finite Element Analysis Part 1, Part 2. So we'll have the next session, same day, same time, Tuesday at 7 p.m. next week. So then we'll discuss the content of week 4 and the related doubt. So I hope you would be there to join me again. Thank you so much again. I will conclude the session now and the meeting. Thank you.